October 31st, 1943. Imperial Japanese Navy Headquarters, Tokyo. Vice Admiral Shigeyoshi Miwa, commander of the 6th Fleet responsible for all Japanese submarine operations, reviewed an intelligence report that had arrived from field agents in neutral Portugal. The document described a new American weapon, an air-dropped torpedo that supposedly could hunt submarines autonomously by listening for propeller noise and steering itself toward the sound. Miwa read the description aloud to his staff of submarine warfare experts. The Americans claim to have developed an acoustic homing torpedo that requires no guidance from the attacking aircraft. The pilot merely drops the weapon in the approximate vicinity of a submarine, and the torpedo locates the target through sound detection and pursues it automatically. The weapon is designated Mark 24, codenamed FIDO. Captain Takao Orita, Chief of Submarine Tactics Development, laughed dismissively. Autonomous guidance? A torpedo that steers itself by listening? This is clearly American propaganda designed to frighten our submarine crews. The technical challenges of such a weapon are insurmountable. How would a torpedo distinguish target propeller noise from its own propeller noise? How would it track a maneuvering target? How would it function in the acoustic chaos of the ocean? This is science fiction, not military technology. Around the conference table, Japan's most experienced submarine officers nodded in agreement. The concept of an acoustic homing torpedo violated everything they understood about underwater weapons. Torpedoes were ballistic weapons, launched on a fixed course toward where the attacker calculated the target would be. Hitting a target required precise calculation of speed, distance, angle, and target movement. The idea that a torpedo could hunt autonomously, adjusting its course in response to sounds it detected, seemed to belong in fantasy rather than reality. Miwa closed the report and filed it with other intelligence documents he considered disinformation. Inform our submarine commanders that American psychological warfare efforts now include fabricated weapon systems designed to damage morale. They should disregard reports of acoustic homing torpedoes as enemy propaganda. What Vice Admiral Miwa didn't know, what Japanese naval intelligence had catastrophically failed to grasp, was that the Mark 24 acoustic homing torpedo was entirely real, had been operational since May 1943, and had already sunk dozens of German U-boats in the Atlantic with near-perfect effectiveness. Within 6 months, these same weapons would begin hunting Japanese submarines throughout the Pacific, turning underwater warfare into a nightmare where evasion was impossible and survival depended on never being detected in the first place. The torpedo that Japanese experts dismissed as fantasy would prove to be one of the war's most devastating anti-submarine weapons, fundamentally changing the tactical equation of submarine warfare. The laughter in that Tokyo conference room would haunt Japanese submarine operations for the remainder of the war, because when your enemy possesses weapons that make traditional evasion tactics obsolete, when hiding underwater no longer provides safety, when your own propellers become homing beacons guiding weapons directly to your hull, submarine warfare stops being about skill and becomes about technological superiority. And in that technological competition, Japan had already lost before the first Mark 24 ever entered the water. To understand why acoustic homing torpedoes shocked Japanese submarine forces so profoundly, we must first examine the state of anti-submarine warfare in 1943 and the seemingly insurmountable technical challenges that made autonomous torpedo guidance appear impossible. Traditional anti-submarine weapons in World War II were fundamentally imprecise. Depth charges were explosives, dropped or launched to detonate at preset depths, creating shock waves that could crush submarine hulls if the explosion occurred close enough. But close enough meant within 20 to 30 feet, and achieving that accuracy required knowing the submarine's exact depth and position at the moment of detonation. Submarines could evade depth charges by changing depth rapidly, turning sharply, or simply moving away from the attacking vessel. Depth charge attacks succeeded through persistence, dropping dozens or hundreds of charges in patterns that eventually bracketed the submarine, not through precision targeting. Hedgehog mortars improved accuracy by launching multiple small charges in a pattern ahead of the attacking ship, detonating only on contact rather than at preset depths. This eliminated the problem of incorrect depth settings and allowed ships to maintain sonar contact during the attack. But Hedgehog still required the attacking vessel to position itself directly over or ahead of the submarine, giving the submarine crew time to maneuver and evade. Aircraft attacking submarines faced even greater challenges. A surfaced submarine could be bombed or strafed, but hitting a small, maneuvering target from a moving aircraft required considerable skill and luck. Once a submarine crash-dived, aircraft had perhaps 30 seconds to drop depth charges or bombs before the target submerged beyond effective depth. The accuracy requirements were brutal. Drop too early and the submarine would be too deep. Drop too late and the target would be out of position. Drop with incorrect aim and the explosion would be too far away to cause damage. The fundamental problem was that all these weapons were ballistic. Once launched or dropped, they followed fixed trajectories determined by physics. They couldn't adjust course to follow maneuvering targets. An attacker needed to predict where the target would be when the weapon arrived and aim at that predicted future position. This gave submarines significant advantages because they could detect attacks, estimate weapon trajectories, and maneuver to avoid the impact point. The concept of a homing torpedo, one that could adjust its course to follow a moving target, had been theorized for decades. But the technical challenges seemed insurmountable in the 1,940 seconds. A homing torpedo needed sensors to detect the target, processing systems to interpret sensor data, and control mechanisms to adjust the torpedo's course. All of this had to function underwater, in salt water that corroded electronics, under pressure that could crush delicate components, while the torpedo itself was traveling at 12 knots and creating its own noise and vibration that would interfere with any detection system. Most impossibly, an acoustic homing torpedo needed to distinguish target noise from its own propeller noise. Every torpedo generates sound through its propeller. How could a system detect the target submarine's propeller while ignoring the sound of its own propulsion? This signal processing challenge appeared unsolvable with 1,940 seconds analog electronics. German engineers had attempted to develop acoustic homing torpedoes for submarine use, creating the T4 Falke and T5 Zonkönig weapons. These torpedoes used passive acoustic sensors to detect ship propellers and steer toward the loudest sound source. They achieved some success against destroyers and escorts, but proved unreliable, often circling back toward the launching submarine's own propeller noise or being deceived by acoustic decoys. The weapons required the launching submarine to flee the area immediately after firing to avoid being hit by its own torpedo. Japanese submarine forces studied German acoustic torpedo development and concluded the technology was premature. The weapons were too unreliable, too easily deceived, and too dangerous to the launching platform. Japanese submarine doctrine emphasized stealth and precision, not experimental weapons with unpredictable behavior. When intelligence reports described American acoustic homing torpedoes, Japanese experts assumed the Americans faced the same technical problems that had plagued German development, making the weapons impractical for operational use. This assessment was completely wrong. American acoustic homing torpedo development took a fundamentally different approach from German efforts. Rather than creating weapons for submarines to fire at surface ships, American engineers designed weapons for aircraft to drop on submarines. This seemingly minor difference solved multiple problems simultaneously. First, an air-dropped torpedo didn't need to worry about its own launching platform. Once in the water, the aircraft was gone. The torpedo couldn't accidentally home on its launch vehicle. This eliminated the circular run problem that plagued German designs. Second, an air-dropped torpedo attacking a submarine had a significant acoustic advantage. Submarines generate substantial propeller noise, especially when maneuvering at higher speeds to evade aircraft. Surface ships also generate noise, but submarines were much quieter when submerged and slow. The acoustic signature difference between a submarine's propeller and the torpedo's own propeller was distinct enough that even primitive 1,940 seconds signal processing could distinguish them. Third, an air-dropped torpedo had a simple mission profile. It only needed to work once, for a few minutes, long enough to detect a submarine within a few hundred yards and steer toward it. Unlike ship-launched torpedoes that might run for miles, the Mark 24 had a short operational envelope where reliability was more easily maintained. The Mark 24 FIDO torpedo resulted from collaboration between Harvard University's Underwater Sound Laboratory, General Electric, and the Naval Ordnance Laboratory. Development began in 1941, parallel to research into sonar and underwater acoustics. The weapon entered production in March 1943 and became operational 2 months later. The Mark 24 was surprisingly simple in design, which contributed to its reliability. The torpedo measured 7 feet 6 inches long, weighed 680 pounds, and resembled a standard aerial depth charge rather than a traditional torpedo. It was propelled by a small electric motor driving a counter-rotating propeller system. The counter-rotating propellers were key to acoustic detection. By rotating 2 propellers in opposite directions, the torpedo reduced its own acoustic signature and vibration, making it quieter than single propeller designs. The acoustic detection system consisted of 4 hydrophones mounted in the torpedo's nose, arranged to provide directional sensitivity. When the hydrophones detected propeller noise from a submarine, an analog amplifier circuit compared the signal strength from different hydrophones. If the sound was louder on the left side, a mechanical linkage adjusted the rudder to steer left. If louder on the right, the torpedo turned right. If equally balanced, it continued straight. The entire system was mechanical and analog, no digital electronics or computers, just clever engineering using 1,940 seconds technology. The torpedo was dropped from aircraft flying at low altitude, typically 200 to 300 feet. Upon entering the water, a parachute assembly detached. The electric motor activated, and the acoustic seeker began listening. The torpedo would circle slowly, searching for propeller noise. Once it detected a submarine, it would steer toward the sound source, accelerating to 12 knots. The effective acquisition range was approximately 400 yards, meaning the aircraft needed to drop the torpedo within a quarter mile of the submarine. This range requirement might seem limiting, but it perfectly matched anti-submarine aircraft tactics. Aircraft located submarines using radar or visual sighting, then flew directly overhead to drop depth charges or bombs. Dropping a Mark 24 inches, the same attack run meant the torpedo entered the water close to the submarine, well within acquisition range. The attacking aircraft didn't need to be precise with aim. They just needed to drop the weapon in the general vicinity, and the torpedo would do the rest. The tactical advantages were revolutionary. Traditional depth charges required accurate aiming and depth settings. The Mark 24 required neither. The pilot simply dropped the weapon near the submarine and departed. The torpedo would find the target autonomously. If the submarine tried to evade by turning, the torpedo turned with it. If the submarine increased speed, the faster propeller noise made it easier to track. If the submarine went deep, the torpedo followed, its seeker tracking the sound down through the water column. The only effective defense was to shut down all propellers and drift silently. But a submarine without propulsion was helpless, unable to maneuver or maintain depth control. The first operational use of the Mark 24 occurred in May 1943 inches the Atlantic, AU-S. Navy Grumman TBF Avenger from Patrol Squadron VP-84 detected a surfaced U-boat and dropped a Mark 24 during its attack run. The torpedo acquired the submarine's acoustic signature, pursued it through 2 attempted evasion turns, and struck the hull near the stern. The explosion broke the U-boat's back. It sank within 2 minutes. The pilot who made this attack, Lieutenant Joseph Maguire, reported that he had simply dropped the weapon and flown away. He didn't observe the torpedo's performance directly, but heard the explosion 30 seconds later. When he circled back, he found only debris and oil. The attack had taken less than a minute from detection to kill, with virtually no opportunity for the submarine to evade. This pattern repeated across dozens of engagements in 1943 and early 1944. Aircraft would detect submarines, drop Mark 24 torpedoes, and the submarines would disappear. The weapons had an astonishing success rate of approximately 37% kills per drop, far exceeding the 5 to 10% success rate of conventional depth charges. More importantly, the psychological impact was devastating. Submarine crews realized that once an aircraft dropped a Mark 24, evasion was nearly impossible. Their own propellers, the very system that allowed them to maneuver and escape, had become homing beacons, guiding weapons to their destruction. German U-boat crews were the first to experience this nightmare. Initial reports of acoustic homing torpedoes were dismissed as crew panic or misidentification of conventional weapons. But as incidents accumulated and survivors described the same pattern, a terrifying picture emerged. Aircraft were dropping weapons that actively hunted submarines underwater. Evasive maneuvers didn't work. Depth changes didn't work. The weapons followed submarines through every attempt to escape, pursuing relentlessly until detonation, or until the submarine managed to drift silently and hope the torpedo lost acquisition. Kapitän-Leutnant Heinz Franke of U-262 survived a Mark 24 attack in August 1943 and provided a detailed report to headquarters. "We were transiting submerged at 80 meters depth when sonar detected propeller noises approaching from astern. The sound was unlike any torpedo we had encountered, very quiet but steady, clearly following our course. I ordered emergency speed and a hard turn to port. The sound turned with us. I ordered reverse turn to starboard. The sound adjusted course and continued closing. We went to silent running, shutting down all non-essential systems. The sound passed within 5 meters of our hull and continued circling. For 7 minutes we drifted in silence while this weapon searched for us. Finally, the sound faded and disappeared. If we had maintained propulsion for even 10 more seconds, we would have been hit. This report and others like it forced German naval intelligence to acknowledge that American acoustic homing torpedoes were real, operational, and devastatingly effective. Countermeasures were attempted. U-boats deployed acoustic decoys, devices that made loud propeller-like noises to lure torpedoes away from the submarine. These decoys had limited success. Some Mark 24 seconds were deceived by decoys, but many ignored them and continued tracking the submarine. The torpedo's signal processing, though primitive by modern standards, was sophisticated enough to distinguish actual submarine propellers from artificial noise sources in many cases. The only consistently effective defense was to avoid detection entirely. If aircraft never located the submarine, they couldn't drop Mark 24 seconds. This forced German U-boats to remain submerged for extended periods, drastically reducing their operational effectiveness. Surface mobility, which had been key to Wolfpack tactics, became suicidal. U-boats that surfaced to recharge batteries or maneuver into attack positions risked immediate destruction by aircraft-dropped acoustic homing torpedoes. By late 1943, the Mark 24 program shifted focus to the Pacific theater. Japanese submarines operated differently from German U-boats, typically conducting long-range patrols and attacking isolated targets rather than coordinating in wolfpacks. But the tactical situation was similar. Submarines needed to surface periodically, and when they did, they became vulnerable to aircraft attack. The first Mark 24 attacks against Japanese submarines began in early 1944. The results mirrored Atlantic operations. Japanese submarines detected by aircraft were hunted with weapons that seemed to pursue them through every evasion attempt. The psychological impact on Japanese submarine crews was even more severe than on German crews because Japanese naval culture emphasized stoic acceptance of danger. When veteran submarine commanders reported that American aircraft were dropping self-guiding torpedoes that couldn't be evaded, and these reports were dismissed as impossible, morale suffered catastrophically. Commander Mochitsura Hashimoto, captain of I-58, encountered a Mark 24 inches, June 1944, while transiting south of the Mariana Islands. His post-war account describes the experience. "We were submerged at periscope depth when the watch reported aircraft overhead. I ordered crash dive to 100 meters. Within 1 minute, sonar detected a torpedo in the water, propeller signature unlike anything we had encountered. The torpedo was circling, searching. I ordered silent running, but our electric motors were still engaged to maintain depth. The torpedo detected us and began closing. I had perhaps 20 seconds to decide. Maintain silence and hope it lost us, or use propulsion to evade but give the weapon a clear acoustic target. I chose evasion. We went to emergency speed and turned hard. The torpedo turned with us instantly, as if connected by wire guidance. We reversed course. The torpedo followed. We altered depth, diving toward 150 meters. The torpedo pursued us down. For 40 seconds we maneuvered while this weapon tracked every movement. Then I heard our chief engineer scream, "Stop engines!" and I immediately ordered all motors shut down. We began sinking in an uncontrolled dive as the torpedo sound passed overhead, circled twice more, then faded away. We used emergency ballast blow to arrest our dive at 200 meters, well past our safe depth limit. Pressure hull plates were buckling from the strain, but we survived. If we had maintained propulsion for 5 more seconds, the torpedo would have hit us. This weapon didn't just hunt submarines, it hunted their propeller noise specifically. The only defense was absolute silence, which meant losing all maneuverability and control. We were not fighting an aircraft, we were fighting an autonomous robot that chased us underwater, and against which all our training and tactics were useless. Hashimoto's I-58 survived this encounter and went on to sink the USS Indianapolis 15 months later, but his assessment of the Mark 24's effectiveness was shared by every Japanese submarine commander who encountered the weapon and survived. The acoustic homing torpedo had made submarine operations infinitely more dangerous by eliminating the primary defensive advantage submarines possessed, the ability to evade attacks through underwater maneuverability. The production scale of the Mark 24 program demonstrates American industrial capacity yet again. Between March 1943 and August 1945, American factories produced over 4,000 Mark 24 torpedoes. These weren't simple weapons. They contained sophisticated acoustic sensors, analog processing circuits, mechanical guidance systems, and electric propulsion units. Yet American industry manufactured them at rates exceeding 150 per month during peak production. For comparison, Germany produced approximately 2,000 acoustic torpedoes of all types during the entire war, many of which were unreliable or dangerous to the launching platform. The strategic impact of the Mark 24 extended far beyond direct kills. Submarines operated under constant psychological pressure, knowing that any detection by aircraft could result in an attack by weapons that were nearly impossible to evade. This fear forced submarines to operate more cautiously, remaining submerged longer, avoiding areas with high aerial patrol density, aborting missions at the first sign of aircraft. The operational effectiveness of submarine forces declined not just because more submarines were sunk, but because surviving submarines achieved less due to the restrictions imposed by fear of acoustic homing torpedoes. Japanese submarine losses accelerated dramatically in 1944 and 1945. While multiple factors contributed to these losses, including improved radar, increased air patrols, and better tactical coordination, the Mark 24 played a significant role. Approximately 68 Japanese submarines were sunk by Allied aircraft during the war. While not all of these kills used Mark 24 torpedoes, intelligence estimates suggest that acoustic homing weapons accounted for at least 30% of aircraft submarine kills where the weapon type could be determined. The true percentage was likely higher because many attacks weren't observed closely enough to confirm weapon type. The technological achievement represented by the Mark 24 was remarkable for 1,940 seconds analog engineering. The torpedo needed to function in a hostile environment, salt water, pressure, temperature variations, while its own propulsion created vibration and noise that could interfere with acoustic detection. The signal processing circuits used vacuum tubes and mechanical linkages. No transistors or integrated circuits existed yet. The guidance system used purely mechanical servos and differential gear assemblies to translate acoustic signals into rudder commands. It was cutting-edge technology implemented with tools that seem primitive by modern standards, yet it worked reliably enough to achieve a 37% kill rate against submarines, an effectiveness level not matched by any other anti-submarine weapon of the era. The comparison to German acoustic torpedo development highlights different engineering philosophies. German weapons were designed for submarine-to-surface ship attacks, requiring long-range, high-speed, and powerful warheads to damage large vessels. These requirements led to complex, unreliable designs that often malfunctioned or endangered the launching submarine. American weapons were designed for aircraft-to-submarine attacks, requiring only short range, moderate speed, and modest warheads sufficient to crack a submarine's pressure hull. These simpler requirements allowed more reliable designs that worked consistently under operational conditions. This pattern, accepting simpler mission requirements to achieve higher reliability, appeared throughout American military technology development. German engineers often designed theoretically superior weapons with capabilities that stressed manufacturing limitations and reliability. American engineers designed adequate weapons with capabilities that could be manufactured reliably at scale. In prototypes and controlled tests, German weapons often outperformed American equivalents. In mass production and field operations, American weapons usually proved more effective because they worked consistently, while German weapons suffered reliability problems. The secrecy surrounding the Mark 24 program was extraordinary. The weapon's existence was classified at the highest levels. Even many Allied personnel didn't know acoustic homing torpedoes existed. Pilots who used Mark 24 seconds were told they were dropping special depth charges without being informed of the homing capability. This secrecy prevented German and Japanese intelligence from developing effective countermeasures during the crucial early deployment period when the weapons had maximum psychological impact. The code name FIDO, while officially standing for nothing, was chosen because it evoked the image of a dog chasing prey, which perfectly described the weapon's behavior. Pilots who observed Mark 24 attacks often compared the torpedo to a hunting dog pursuing a rabbit, turning and adjusting course to follow the submarine's movements with uncanny accuracy. This anthropomorphization made the weapon seem even more frightening to submarine crews, who couldn't understand how an inanimate object could track them so precisely. Post-war interrogation of Japanese submarine officers revealed deep psychological trauma associated with Mark 24 attacks. Commander Zenji Orita, who survived multiple war patrols despite 3 separate encounters with acoustic homing torpedoes, described the experience in his memoir. Depth charges were frightening, but predictable. You could calculate where they would explode based on the attacking ship's position. You could maneuver to avoid the most dangerous positions. Acoustic homing torpedoes were terror incarnate. They hunted you. They followed you. Every turn you made, they matched. Every depth change, they pursued. Your own submarine, the machine that kept you alive, had become your greatest vulnerability because its propellers attracted the weapon that would kill you. The worst part was the helplessness. Against depth charges, skilled submarine commanders could evade through superior seamanship. Against acoustic homing torpedoes, skill meant nothing. The only defense was to shut down and drift silently, hoping the weapon lost you. But a submarine without propulsion is not a submarine. It's a coffin waiting to sink, or a target waiting to be depth charged. We went from hunters to prey, and the weapon hunting us was relentless, tireless, and nearly impossible to deceive. This psychological transformation, from confident predators to terrified prey, exemplified the Mark 24's strategic impact. Japanese submarine forces never recovered their offensive capability after mid-1944. Not because all their submarines were sunk, but because surviving crews operated under such fear that their effectiveness degraded dramatically. Submarine warfare requires aggressive risk-taking, closing to attack range despite danger, accepting calculated risks to achieve torpedo firing positions. Crews terrified of acoustic homing torpedoes couldn't operate aggressively. They avoided contact, aborted attacks early, and accomplished far less than their numerical strength suggested. The technological lineage of the Mark 24 extends directly to modern anti-submarine warfare. Every modern, lightweight torpedo, whether dropped from aircraft, launched from surface ships, or deployed from submarines, uses acoustic homing guidance derived from the Mark 24 concept. The sensors are digital rather than analog, the processing uses computers rather than mechanical circuits, and the range is measured in miles rather than hundreds of yards. But the fundamental principle remains identical. Detect the target's acoustic signature, process the signal to determine direction, steer toward the target, and detonate upon contact. The Mark 24 program also validated a broader strategic concept. Autonomous weapons systems could be effective, force multipliers, even with relatively primitive technology. The torpedo didn't need sophisticated artificial intelligence or advanced computing. It needed adequate sensors, simple but reliable processing, and a mission profile that matched its capabilities. This lesson influenced post-war military technology development across multiple domains, from guided missiles to smart bombs to autonomous drones. Today, the National Museum of the U.S. Navy displays a Mark 24 torpedo, one of the few surviving examples. Museum visitors who examine the weapon often express surprise at its simplicity. The external appearance is unremarkable, a cylindrical tube with small control surfaces, more resembling a practice torpedo than a revolutionary weapon. But the internal components, primitive vacuum tube amplifiers and mechanical differential gears, represent genuine innovation. Engineers created a functional autonomous homing system using 1,940 seconds technology, solving problems that seemed unsolvable to their contemporaries. The final validation of the Mark 24's effectiveness came from an unexpected source. In 1955, the Japan Maritime Self-Defense Force began training exercises with the U.S. Navy. During one exercise, American aircraft demonstrated simulated Mark 24 attacks against Japanese submarines. The Japanese submarine commanders, several of whom had survived World War II combat, requested that the demonstrations stop because the exercises were too realistic and traumatic for crews who had experienced actual acoustic homing torpedo attacks during the war. The psychological scars remained a decade after the war's end, a testament to how profoundly the weapon had affected those who survived encountering it. Vice Admiral Shigeyoshi Miwa, the same officer who had dismissed intelligence reports of acoustic homing torpedoes as propaganda in October 1943, testified at post-war hearings about Japanese submarine operations. His testimony included this assessment. The American acoustic homing torpedo was the most devastating anti-submarine weapon deployed during the war. Not because it sank more submarines than other weapons, though its success rate was very high, but because it fundamentally changed the tactical equation. Before acoustic homing torpedoes, submarines could evade attacks through skillful maneuvering. After their introduction, maneuvering became the action most likely to attract these weapons to your position. Submarines had to choose between maintaining mobility and being hunted by weapons that followed propeller noise, or remaining silent and helpless without propulsion. I dismissed the early intelligence reports because the described capability seemed impossible with available technology. I was wrong. The Americans had solved technical problems we considered unsolvable. When Japanese submarine forces encountered these weapons operationally, the psychological damage was severe. Crews knew that any detection by aircraft might result in an attack by a weapon they couldn't evade. This knowledge destroyed the aggressive mentality necessary for effective submarine operations. We became cautious when we needed to be bold, defensive when we needed to be offensive. The acoustic homing torpedo defeated us psychologically before it defeated us physically. This admission from Japan's submarine force commander provided complete validation of the Mark 24's strategic impact. The weapon German experts said was impossible, and Japanese admirals dismissed as propaganda, proved to be one of the war's most effective anti-submarine systems, fundamentally changing underwater warfare in ways that remain relevant today. When Vice Admiral Miwa laughed at those intelligence reports in October 1943, he was laughing at a technological achievement that would help defeat his submarine force. The weapon he dismissed as fantasy was already operational, already sinking German U-boats, and would soon be hunting Japanese submarines throughout the Pacific. His laughter reflected a failure to understand that American engineering had advanced beyond what Japanese experts believed possible, that acoustic signal processing could work with 1,940 seconds analog technology, and that autonomous weapons systems could be effective without requiring human guidance. That laughter died in the Pacific Ocean, silenced by the same acoustic signatures that guided Mark 24 torpedoes to their targets. Japanese submarines that might have threatened Allied supply lines, disrupted operations, and sunk warships, instead spent their time hiding, evading, and ultimately dying, hunted by weapons that turned their own propellers into homing beacons, broadcasting their locations to relentless pursuing torpedoes. The impossible weapon laughed at by admirals became the nightmare that haunted submarine crews, proving once again that in modern warfare, technological innovation defeats tactical tradition when the innovation is well designed, properly deployed, and produced at scale. The Mark 24 acoustic homing torpedo stands as testament to several crucial lessons of World War II. That weapons don't need to be perfect to be effective, they need to be adequate for their specific mission. That American industrial capacity could produce sophisticated weapons in large quantities when properly organized. That psychological effects often exceed physical effects when weapons create tactical situations where traditional defenses don't work. And that dismissing enemy technological claims because they seem impossible is a dangerous error that can prove strategically fatal. The Japanese admirals learned these lessons, but only after their submarine force had been decimated by weapons they insisted couldn't exist. The submariners learned these lessons by experiencing Mark 24 attacks and understanding that their propellers, the very systems that gave them mobility and control, had become the signatures guiding their destruction. And historians learned these lessons by studying how a relatively simple torpedo, designed with 1,940 seconds technology and produced in thousands of units, helped win the anti-submarine campaign by making submarine operations psychologically unbearable, even for veterans who had survived years of combat. When the acoustic homing torpedo entered the water after being dropped by aircraft, when its hydrophones began listening for propeller noise, when its guidance system detected a submarine and turned the torpedo toward its target, it demonstrated that autonomous weapons could hunt and kill without human guidance, that acoustic detection could work underwater despite all the interference and noise, and that American engineering could solve problems that enemy experts declared unsolvable. And in doing so, it wrote the first chapter of modern guided weapons technology, a chapter that began with submarine commanders dismissing it as propaganda and ended with those same submarines sinking under the Pacific, pursued to their deaths by weapons that hunted them through total darkness, using only the sound of their own desperate attempts to escape.